So we're asked to find the instantaneous velocity at this many seconds, at 0.8 seconds. And so to find the instantaneous velocity, to get a picture of it, I'm drawing like a quick graph right here to show you guys what this function looks like. And this is a function that helps us calculate its distance, okay, from wherever it's dropped, or to calculate its distance. And so we're going to say that this is 0.8 right here. So at 0.8 seconds, we want to find the instantaneous velocity, which means we're going to have to find the slope of the tangent line to that point. But we're only given 1 point. And so how do we find that slope of that line? We only know 1 point. We could find that point pretty easily, actually. We just have to go and plug 0.8 into the function. So this would be 0.8 would be your x, and then to find the y, we would take 0.8 and we'd plug it into the function. So it would look like this, 0.8, and there you have it. Can someone do that really quick? Can you plug 0.8 into that function to tell me an approximate y value right there? 0.64?
No, times 4.
3.136? Okay, so at that point, at this point, what is the slope? And this point right here is right there. Okay, what is the slope at that point? And the way we do that is we find the slopes of the secant lines that lead up to that point. So this is where the approximation stuff comes in. Yeah, well, you're trying to notice a trend. Okay, so let me explain a little farther. We're going to find another point on this line so that we can find the slope of that secant line. And I don't want to pick a point that's too far from this point. I want to pick a point that's actually pretty close to it. And then I'm going to pick another point that's even closer. And then I'm going to pick another point that's even closer, so I can see what's happening to the slope as I'm getting closer and closer. So here, let me explain. We have a t right here. So let's go. In this case, let's go above 0.8. So let's go 0.9. Just a point that's right next to it. And so to find 0.9, we're going to have to plug that, or to find the points, we're going to have to plug that into our function. Can you guys do that really quick? 3.969. Okay, that's what you got. So that's now I'm going to increase like our scale here. I'm going to say this right here is 0.9. This is just for visual purposes. And so this is that point right there. And so this line right here goes and hits the curve twice. So we can find the slope of that line, a secant line. Right? You guys know how to find the slope of that. Thanks for the yawn. Okay, so we have a point right here, and we have a point right here. Now we can find a slope. So we just, let's see, I'm going to write it out with function notation. So my x value for the first one is 0.8. My y value is f of 0.8. And I'm going to subtract the x value on the bottom, which is 0.9, and the y value on top, which is f of 0.9. Now some of you guys might be going, why is he writing the f? Why doesn't he just write the y? Yeah, I can. I'm just trying to show you guys another way to write it. Because in a second, I want to show you guys visually what this looks like on Desmos. And so we're going to write it like in function notation. So Desmos actually figures it out for us. So this is going to be 3.136 minus 3.969 all over 0.8 minus 0.9. Can you guys plug that in? Tell me what you get. So our slope at this point, these 2 points, is 8.33. Okay, does it keep going? It's just 8.33? Okay, so this is our slope for this line right here. M equals 8.33. That's our velocity for that line. But that's not the velocity for the purple line, the tangent line, which is what we're looking for. And so what we're going to do now is we're going to find a point that's even closer than 0.9 and plug that in. So instead of 0.9, let's plug in 0.99. It's kind of annoying, right?
Isn't that far?
Oh, wait, thank you. Not 0.99, it'd be 0.85. I'm just seeing if you guys are paying attention there. Okay, 0.81. Yeah, that'd be nice. Okay, and then what? Give me the next x value that would be even closer. 0.8. It'd be 0.801. Okay, and the point closer to that would be 0.8001. Okay, now I'm gonna stop right there. I'm not actually gonna do that many. I'm just saying we can get points closer and closer and closer to help us find the trend here. And so now we're gonna have to find the y value here, the y value here, and the y value here to find those three slopes of those three secant lines to notice a trend. This is very annoying. And I thought about that too, and I thought, okay, I'm going to explain this to my students, and they're going to say, why are we doing this? And that's exactly what you said. Because I would think the same thing. Isn't there a faster way to do this? And that's exactly what I want you to think, because there is a faster way to do this, and we're going to learn how to do that, because you can't appreciate it unless you do this first. Okay? So, let's fill in these y values really quick and find the other slopes. I'm just going to write them up here. So here's your y values. Oops. Your y values are right here. And here's your slopes. Okay, we started with this secant line right here. That's 8.33. And then it drops down to 7.889. And then 7.8449. And then 7.84049. So you can kind of see where this slope is converging. So we could say for our answer here that the slope of the tangent line equals approximately, yeah, we should put approximately right here, 7.8. Because, oh yeah, you can put the 4 too. It's going to continue to get closer and closer to that number. So what's the slope of our tangent line here? It's 7.8. And that was very tedious and kind of annoying too. You're going to see a couple of these problems for your practice tonight. But guys, if you get the gist of it, you can skip over a couple of problems so you don't have to spend so much time like finding all these slopes. But you got to do it at least twice. Okay, so for two different contexts, you need to list out some points and find the slopes of those secant lines so you can notice a trend to find the approximate slope of the tangent line. You guys understand?
Yeah.
Okay. I think that if you can visualize something, that you can have a better understanding of it. So I want to look at the problem we were just looking at. So let's graph the function that we were working with, which was 4.9 times x squared. Now we have to use x here because that's how Desmos works. I kind of want my window to look a little like my curve right here to look a little wider, so I'm going to go ahead and change my my window to something like that. Okay, and I can change my x-axis actually to be closer together. Let's see. We'll say that's 5, and this is going to be -5. All right, so I made it a little wider just because of preference, and then we wanted to we want to graph the point that it wants the instantaneous rate of change. So to graph the point at the instantaneous rate of change, our x value was 0.8, comma, and a really neat thing about Desmos now is that it has f defined. So you see f right here, it's defined as this function. So that means over here for our y value, we can say f of 0.8, and it finds the value for you. If you click on the point right here, it'll show you what the y value is. It finds it for you. So here's the point, and what we want to do is we want to find the instantaneous rate of change at that point. So we want to find the slope at this point. So check out what we can do. We can actually make a line, a linear equation right here using we'll use point slope form to guesstimate what our slope's going to be. So actually here, let me put this on projector mode. All right, so here is point slope form. Y minus Remember how it's y minus y1 equals m times x minus x1? So what we need here is we need a y and an x. So the point that we have is f of 0.8 for the y, and then the x is 0.8. And then go ahead and click on the m right here to add a slider. That m represents the slope. So what you're going to do here is you're going to try to move your slope here so that you get a roughly tangent line. Now remember, we found it to be like 8 or 7 point something, right? Was it 7.8? So right there. Whoops. So does that line look tangent? Yeah, and you can actually have fun with it. We could change this slope. We could just let this slope go, and we can make our line dance for us. So this slope right here is the instantaneous rate of change because that's the slope of this tangent line. And we found 7.8 by finding a trend and estimating. Okay, and here you could actually try to find it too by moving your slope around to find the line that would be more tangent. Okay, all right.